Here's our final example that we're going to have for section 4.1 and 4.2 before we move forwards. So we have a linkage is made of 3 pin-connected steel members, each having a diameter of 1 1/4 inch. If a horizontal force P of 60 kips is applied to the end at B of member AB, determine the displacement of point B. So as I pull on this link, it's going to have that tendency to stretch. So we're going to get a delta B, okay? As we apply this axial load then to these two diagonal links, they are also going to follow that same X direction. However, again, like example 6, their change in length is not going to be a direct one-to-one relationship to how much they move. So we are going to note that these are all two force members. So I could use method of joints here if I know force P. Okay, so it's got to be equal and opposite. So we're pulling force P here as well. We could use method of joints to figure these out. We can also note that they are symmetric. So I know that they're going to carry the same amount of force as we're moving through. So let's go through here and figure out what we have. We know that we have delta equals PL over AE, which is it's just all of our equations kind of lumped together. We know these are pin connected, so this would be a great exam question because we could go back and ask you about the design of the pins, if they were in single shear or double shear, because all of these there's 3 pins in this system. And so there's, yes, lots of things we could check. So we have a linkage of 3. So our members are all made of the same thing. They are made of A992 steel. And I'm going to get my book out so we can get our values. So I'm going to note that I am in feet, kips. So we're in the U.S. customary. And we are looking at A992. Where are we? Steel. And look at this mess I have in my book from circling and showing you all. Okay, so if I'm coming across A992, so my modulus of elasticity is 29.0 times 10 to the third KSI. And my yield strength, that looks like 50, whether it's in tension or compression, and that's also KSI. So we have a yield stress of 50 KSI. So we need to make sure we're below that, otherwise we need to find a stress strain curve. We have a modulus of elasticity. I already forgot what it was. A992, 29. So we have 29 times 10 to the third KSI. Remember it said times 1,000. Okay. So we have that, and they have a diameter. So our area is going to be pi over 4 diameter, 1 1/4 inch squared. Okay, this force P is 60 kips. And if we look at this, we have original lengths. So for bar AB, so the length original of AB is 6 feet. And I'm going to go ahead and change that into inches so I don't forget. So I have 12, 24, 36, 48, 60, 72 inches. Okay, and then the lengths of AC and AD, and it's symmetric, so we're going to just go back. I know that this is 3 feet, 4 feet, so the length of this has to be 5 feet, which is 12, 24, 36, 48, 60 inches. Okay. So now I can go back and I can calculate. I've got P for AB, length of AB, A of AB, E of AB, and then I've got, well, we haven't determined yet P, and we'll have to do that. So let's always start with, what do we always start with? We always start with a free body diagram, and we look at equilibrium. So I know that delta B is going to come from the change in length of AB plus some sort of delta that comes from this linkage moving, plus something from AC, but it's not going to be all of AC, right? It's going to be part of AC. So free body diagram. If I start here at B, I have 60 kips. And let's pull back 60 kips. Well, actually, let's do this correctly. And let's do force of AB. And I know that it's going to be in tension because we're pulling, so the force of AB is indeed 60 kips. And then I can look at A, and I have 60 kips, and I have the force in AD. I have the force in AC, and they are at a 3, 4. So I can sum forces in the x direction equals 0, and I'm going to have 3/5 force AC plus, actually minus, because they're going backwards, minus 3/5 force AD plus 60 kips equals 0. And I know that they are the same amount, right? They're the same amount, so they are equal to each other, so we can just also call this one force AC because it's like we have double. So I'm going to have minus 3/5 plus 3/5 is 6/5 force AC plus 60 kips equals 0. So force AC equals, so we've got 60, and then we're going to be times 5, 6. So 60 divided by 6 is 10, times 5 is 50 kips. And this is also in tension, so it's going to be a positive delta. So we have our force in AB, and we have our force in AC. Okay, so now let's go back and let's look at the deformation, because this is where it again gets very, very tricky. But if you can draw a big picture, then it's easier to see. So let's start with the delta of AB. So I know that delta AB equals PL over AE, and it is going to be going in that x direction, So I have my internal force of 60 kips. I have my original length in this nice, we have everything written out, 72 inches. Cross-sectional area, pi over 4, 1.25 inches squared, and an E of 29 times 10 to the third. And let's get that multiplied out. So we have 60 enter, 72 times, pi as a number, 4 divided by 1.25 times, 1.25 times, 29 e to the third times, divided by, and I get 0.1214 inches going to the right. Now, what I really ought to do first is I should check for yielding. And when I'm checking for yielding, the force in AB is much bigger than the force in, well, not much bigger, but it is bigger than the force in AC and AD. So if we were checking yielding, we would check the yielding here, because if AB is fine, the rest of it's fine. So how do we check yielding? Stress equals P over A. Okay, stress equals P over A. So I have a force of 60 kips, and then I have an area, pi as a number, so 4 divided by, and then 1.25 times, 1.25 times, and then divide it, and I get that we have a stress of 48.89 KSI, which is less than 50 KSI, that I found in the table. So we are good to go. We are in the elastic region. Okay, we are in the elastic region. Okay, so now that we have that, we need to talk about what's happening up here. So I'll try to have all of this on here. So here is C, okay? And then we come down and we're going to go over, and here is, okay? So here is our original C, C to A. And then as we pull this, because it's symmetric, okay, we are going to end up stretching along this same line here. So let's see if I can get this kind of drawn in. So we're going to have this stretch, okay? And it's going to go towards the right, just like the force is pulling it. So we have something that looks like this, A to A prime. And I know that this is the delta AC that I'm looking for. I also know, because it's symmetric, whether I did AC or AD, it's going to be that same amount of stretch. So I'm just going to look at the top right now. So I don't know what that is, okay? I do have Okay, we're back to a triangle. And if we go back to a triangle and we need to have something, we have to go back into the recesses of our brains of how we can associate sides and angles when we're not looking at a right triangle. So I know that A to C, okay, I know that A to C is 60 inches. And I know that C to C to A prime is, well, we haven't found that. So let's go ahead and find the new length of C to A prime. So we're going to have, as we're pulling on that, okay, as we're pulling on that, I'm going to have a change in length of AC. And that's just going to be PL over AE. And that internal force was 50 kips. Its original length was 60 inches. Its area is pi over 4, 1.25 squared, and it has a modulus of elasticity of 29 times 10 to the third. So when I multiply this out, okay, I have 50, 60 times, pi as a number, 4 divided by 1.25 times 29 e to the third times, and divided by. And I get a delta of, okay, 0.084. 0.08429 inches. And if I want to know then this final length, that final length, when I'm looking at A prime to C, so C to A prime, C to A prime, I know that's going to be the original length of 60 inches plus the change in length. So let's add a 60 to that, plus, and I get 60.08429 inches. Okay, so let's mark that here. So we have 60.08429 inches. So I now have two sides and I need another side, but I don't have an angle. I don't have an angle. So what do I know? Well, I know this is 4 feet and this is 3 feet. So I could actually calculate this angle theta. Okay, tan theta equals opposite over adjacent. So theta equals, we have 4 enter, 3 divided by, okay, and then we have to do inverse tan, and we get 53.13 degrees. And if I know theta, can I calculate this internal phi? Okay, can I calculate phi? 180 degrees minus theta equals phi. So we're going to change signs, add 180, 180, and I get 126.87 degrees. Okay, so now I have an internal angle. So this time I have two sides and an internal angle. Two sides and an internal angle. Last problem we had three sides. Three sides, we can use law of cosine. This time I have two sides and an angle. And with law of sines then, if I'm looking at law of sines, then I can say that sine phi, okay, sine phi is to, okay, because really I need to get this delta. I really need to get this delta. But I don't know this side and I don't know this angle associated with it. So let's just work on what we do know. I know a side. I don't know the angle opposite it, but I know a side, and now I know this angle. So let's work on this angle right here. Let's just call that beta, okay? And this was phi. So sine phi is to 60.08429 inches as sine beta is to 60 inches. Okay, sine beta is to 60 inches. And when we do this, I can calculate then that my angle beta is, so I have sine phi, which is 126.87, so that's sine, divided by, okay, divided by 60.084297, okay, times 60, inverse sine, and I get 53. I get that beta is 53.02 degrees. Okay, so now if I know that beta is 53.02 degrees, and I know this angle phi, which this is really kind of hard to see that that's an angle phi, but let's redo it, angle phi. Okay, can I calculate this angle right here, which we can call alpha? Can I calculate alpha? Can I calculate alpha? How can I calculate alpha? Well, how many degrees are in a triangle? Okay, I know that. Let's come back over here now. I know that there are 180 degrees in a triangle. So I know that alpha has to be 180 degrees minus beta minus phi. So let's take 180. We have 180 minus beta minus phi, and I get a very, very, very tiny number. Okay, I get a very, very tiny number. So let's make sure that we have that in there correctly. So phi was 126.87, and then we had 53.02 plus, and then we're going to change signs, and we're going to add that to 180, and we get 0.11 degrees. So alpha equals 0.11 degrees. Now, if I know alpha, can I get this little delta guy right here? Can I get that delta? I sure can, because I can now use law of sines again, and this time I can say that beta, sine beta is to 60 as sine alpha is to the delta that I'm looking for in the x direction. So let's start with that. So sine of 0.11 degrees is to delta AC, and we're circling it because it's not the true length, okay, as sine of 53.02 degrees is to 60 inches. So when I calculate this out, I'm going to get that delta AC, we're circling it because it's not the true length, it's now the displacement of A to A prime. I guess we should call it A to A prime. How about we do that? We just call that A to A prime, delta of A to A prime. Okay, so I'm going to get 0.11 sine, and I'm going to cross multiply, so 60 times 53.02 sine divided by, and I get delta AC, well, delta A to A prime is 0.1442 inches, okay? And now when I add that up with the delta I got from AB, I now know that delta from B to B prime, remember it equals delta A to B plus delta A to A prime, and I'm going to get 0.1442 plus 0.1214, and I get a total displacement of B to B prime equals 0.2656 inches to the right. And it's important to signify which way it's going in case anything is in compression. So there you have it. That is using law of sines and just working our way through a triangle to figure out what it is we need to know.